Today we explore the fascinating colloidal physics behind ramen broth, where food science meets materials engineering. Ramen broth is a complex colloidal emulsion containing millions of microscopic fat droplets suspended in an aqueous phase enriched with dissolved proteins. Let us first understand what colloids are and why ramen broth qualifies as one. A colloid is a mixture where particles ranging from 1 nanometer to 1 micrometer are dispersed throughout a continuous medium without settling out. Particle diameters must fall between 1 nanometer and 1 micrometer to exhibit colloidal behavior. This diagram shows the 3 categories of mixtures based on particle size: solutions with particles under 1 nanometer, colloids from 1 nanometer to 1 micrometer, and suspensions with particles over 1 micrometer. Ramen broth contains fat droplets typically ranging from 0.1 to 10 micrometers in diameter, placing them squarely in the colloidal regime. The foundation of great ramen broth begins with collagen extraction from bones and connective tissue. Collagen has a distinctive triple helix structure, with 3 protein chains wound together in a rope-like configuration stabilized by hydrogen bonds. Collagen is the most abundant protein in animal connective tissue, comprising about 30% of total body protein in mammals. When heated in water, collagen undergoes hydrolysis, breaking down into smaller gelatin molecules that dissolve into the broth. This collagen extraction requires temperatures above 70 degrees Celsius maintained for several hours to sufficiently break the molecular bonds. Let us examine what happens during the long simmering process that creates tonkotsu, or rich chicken broth. Traditional tonkotsu broth requires simmering at 95 to 100 degrees Celsius for 12 to 18 hours with constant agitation to maximize extraction. Question: why does longer cooking produce cloudier, whiter broth? Let us examine the physics behind this transformation. Answer: extended heating breaks down more collagen and emulsifies more fat into progressively smaller droplets that scatter light more effectively. Light scattering intensity is proportional to 1 over wavelength to the 4th power times particle diameter to the 6th power, according to Rayleigh scattering theory. Now we examine how mechanical agitation emulsifies fat droplets into the aqueous broth phase. Mechanical agitation applies shear forces to large fat droplets, breaking them into progressively smaller daughter droplets through a process called turbulent emulsification. The Weber number, a dimensionless parameter, governs whether droplets will break up under given flow conditions. The Weber number equals density times velocity squared times diameter divided by surface tension. When the Weber number exceeds a critical value around 1, inertial forces overcome surface tension, and droplets break apart into smaller fragments. Dissolved gelatin molecules play a crucial role in stabilizing the fat and water emulsion. Gelatin molecules absorb onto fat droplet surfaces, with hydrophobic regions anchoring into the oil phase and hydrophilic regions extending into the water phase. Gelatin acts as an amphiphilic emulsifier, possessing both hydrophobic and hydrophilic domains that allow it to stabilize oil-water interfaces. The free energy of adsorption equals surface tension times area minus temperature times entropy change, driving gelatin to coat droplet surfaces. This adsorbed gelatin layer creates a substantial energy barrier that prevents droplet coalescence and maintains emulsion stability. Temperature profoundly affects the size distribution of emulsified fat droplets in the broth. This graph shows how average droplet diameter decreases with increasing temperature, as higher thermal energy promotes more efficient emulsification down to a minimum size. Higher temperature reduces both liquid viscosity and interfacial surface tension, making it easier to break droplets into smaller fragments. Viscosity follows an Arrhenius relationship, equaling a reference viscosity times E to the activation energy over RT. At 95 to 100 degrees Celsius, optimal conditions exist for creating sub-micrometer droplets that produce maximum opacity. The characteristic cloudy white appearance of tonkotsu broth arises from mie, scattering by colloidal fat droplets. When light strikes colloidal droplets comparable to the wavelength, it scatters in all directions through mie scattering, creating the opaque white appearance. Turbidity quantifies the amount of light scattered per unit path length through the medium, measured in nephelometric turbidity units. Turbidity equals 3 times volume fraction times scattering efficiency, divided by 2 times droplet diameter. For high-quality ramen broth, turbidity typically ranges from 100 to 1,000 nephelometric turbidity units, indicating heavy colloidal content. Understanding droplet coalescence is critical for maintaining emulsion stability over time. When two droplets approach each other, they can collide and merge into a single, larger droplet through coalescence, driven by the reduction in total surface energy. The overall coalescence rate depends on both the collision frequency between droplets and the probability that a collision results in merging. The rate of change of droplet number concentration equals negative K times concentration squared, showing second-order kinetics. Question: what prevents all droplets from eventually coalescing into a single large oil layer? The answer lies in the protective gelatin coating. Gelatin provides steric stabilization, creating a physical barrier that prevents droplet contact and fusion. The adsorbed gelatin layers on approaching droplets create overlapping polymer brushes that generate a repulsive steric force, preventing direct contact. The steric interaction potential equals Kt times L over d squared times e to the negative h over L, where h is separation distance. This steric repulsion must exceed thermal energy Kt by several orders of magnitude to reliably prevent coalescence over the lifetime of the broth. Rapid cooling can destabilize the emulsion through multiple mechanisms, breaking the carefully established colloidal system. Compare hot stable broth with many small dispersed droplets to cold broken broth, where droplets have coalesced into fewer larger globules that may separate. Cooling dramatically increases viscosity, which reduces Brownian motion and allows density-driven creaming to concentrate droplets at the surface. Stokes velocity equals 2r squared times density difference times g divided by 9 times viscosity, governing the creaming rate. Below 35 degrees Celsius, gelatin molecules form a weak gel network that can trap droplets but also create stress concentrations, promoting coalescence. Reheating previously cooled broth involves complex transitions that can either restore or further damage emulsion quality. This phase diagram shows the gel-to-sol transition as temperature increases, with gelatin network melting above 35 degrees Celsius. If significant coalescence occurred during the cooling phase, reheating cannot restore the original fine droplet size distribution, resulting in permanent quality loss. Multiple freeze-thaw cycles cause progressive and cumulative degradation of emulsion quality through repeated coalescence and ice crystal damage. The subjective sensation of mouthfeel can be quantified through rheological measurements that characterize flow behavior. 3 key parameters define ramen broth mouthfeel: body from viscosity, creaminess from fat content, and coating ability from protein content. Effective viscosity equals base viscosity times 1 plus 2.55 plus 10.055 squared, the Einstein Batchelor equation for dilute suspensions. For typical tonkotsu broth with volume fraction 0.05, this gives a viscosity enhancement factor of approximately 1.4 times the base value. The same physics governing ramen broth applies to numerous industrial emulsions, from paints to pharmaceuticals. Paints, cosmetics, pharmaceutical formulations, fuel emulsions, ramen broth, and milk all share identical colloidal physics principles. All these systems are stabilized by amphiphilic emulsifiers that create steric or electrostatic barriers, preventing droplet coalescence. All exhibit similar failure modes, including creaming, flocculation, coalescence, and Ostwald ripening, which engineers must prevent. Ostwald ripening represents a subtle but important long-term instability mechanism in colloidal emulsions. In Ostwald ripening, oil molecules diffuse through the continuous phase from smaller high-curvature droplets to larger low-curvature droplets. The Laplace pressure difference equals 2 gamma over r, making small droplets have higher internal pressure than large droplets. This pressure difference drives a chemical potential gradient, causing net molecular diffusion from small to large droplets over time. Average radius cubed grows linearly with time, according to the Lifshitz-Slozov-Wagner theory of Ostwald ripening. Understanding the physics allows us to determine the optimal serving temperature for maximum sensory appeal. Sensory quality peaks around 75 to 85 degrees Celsius, balancing emulsion stability, aroma release, and comfortable consumption temperature. At 75 to 85 Celsius, the emulsion remains stable. Gelatin is fully dissolved. Fat is fluid, and aroma volatilization is optimal. Below 60 Celsius, gelatin begins gelling, viscosity rises excessively, and the mouthfeel transitions from creamy to slimy and unpleasant. Let us perform a detailed numerical calculation to estimate droplet concentration in tonkotsu broth. Given that 100 milliliters of broth contains 5 grams of fat with average droplet diameter of 1 micrometer, fat density is approximately 0.92 grams per cc. Fat volume equals mass over density equals 5 divided by 0.92 equals 5.43 cubic centimeters. Single droplet volume equals 4/3 pi r cubed equals 5.2 4 times 10 to the negative 13 cubic centimeters. Total droplet number equals total fat volume divided by single droplet volume equals 1.04 times 10 to the 13th droplets. This means over 10 trillion individual fat droplets are suspended in just 100 milliliters of tonkotsu broth. The enormous interfacial area created by emulsification has important thermodynamic and kinetic implications. Total surface area equals number of droplets times 4 pi r squared for each droplet. This equals 1.04 times 10 to the 13th times 4 pi times radius squared equals 3.27 times 10 to the 5th square centimeters. This translates to approximately 33 square meters of interfacial area contained within just 100 milliliters of broth. The surface energy equals surface tension times area equals 3.27 joules, representing the thermodynamic cost of creating this interface. This massive interfacial area requires substantial quantities of gelatin or other emulsifiers to absorb and stabilize effectively. Different ramen broth styles exhibit different colloidal characteristics reflecting their preparation methods. Tonkotsu has the highest droplet density with smallest size. Patan is intermediate, while Chintan clear broth has minimal emulsified fat. Tonkotsu broth has volume fraction around 0.05 with average diameter 1 micrometer. Patan broth has volume fraction around 0.02 with average diameter 2 micrometers. Chintan broth has volume fraction around 0.01 with average diameter 5 micrometers.